Bismillahirrahmanirrahim. We continue our discussion on processes and discuss the operations on processes. We had already covered in previous lectures are with the process, how it is different from job. Then we discussed different process states, and the state transitions have already been discussed. We also discussed what is process control block and processes. In previous lecture we said there are some of the operations that need furthermore elaboration. So in today's discussion, we will be revisiting operations on processes to see what complicated operations are there in order to have a better understanding of them. So the point that we are going to start in today's discussion is some of the operations that either user can perform on process or operating system can perform. We will be discussing some of them in further more detail. Process creation is an operation, as we said in previous lecture, that a user can perform on process when you click Start New. Within any application, that means you have created a new application. For example, if within Word document you click File New, that means you have created a new Word application. Now, there is little more to discuss within process creation. For example, in some cases, a running process can create children processes. And this is the phenomena in operating system terminology, we call it fork. Forking is a function of operating system in which a running process creates children processes. Now, how a running process or parent process create children? For example, you might have visited some website, and within that website you might have clicked some other link or clicked some tab that have led you to some other website or some other location within the same website. So actually a running process has created children in which you have jumped from one location, the parent process, to another location, to some other website or to some other location within the same website. So 2 or 3 or 4 or multiple processes are then started to execute at the same time. And this is because the parent process was able to create further more processes that are known as the children processes. You might have used the same thing in programming as well. For example, the main function, you might have created multiple functions within the main function. Some of them are system-defined functions such as cin, cout. When you call a system-defined function or a user-defined function, for example, you have defined function A, B, C within the main function. That means main function is the parent function, parent process, and when it starts executing, it then generates children functions. For example, when there is a cin input statement, cin function or cin process is called, or when there is a jump to some of your defined function. For example, function A has been called, which you have defined somewhere else. So the main function has created another child function with the name A. So there would be a jump to another location within memory. and that function A will start executing. So a running process is creating children processes. Unless and until you run the parent process, you are not able, or you might not know what other children functions may be required to be run. So the children processes are dependent on the parent process. Once parent will execute, only then you will come to know about some other children processes. If there is no parent, you are not able to execute or to know what children processes are hiding within that main process. So process creation is not very simple. If it is a single process, then it is quite very simple. But if a heavyweight process is there which allows you to execute further more children processes, so this becomes quite complicated, as the child process would now require the same resources as they have been required by the parent process. The children process would require memory space within RAM, the children process would require CPU, the children process would require the other resources such as input-output resources. So it would be then considered as full processes that would require resources from operating system to complete the execution. So when there is forking, the process creation becomes quite complicated, as operating system now has to not only deal with the parent process, but also it has to deal with all the children it has created. Now, how resources are shared between the parent and its generated children processes. So different situations can be there. For example, whatever the resources parent has obtained, those resources are then shared among the children of that parent. So a parent process shares its own resources among its children. For example, if a parent process has been assigned 20 millisecond CPU time, now that 20 millisecond will half be utilized by the parent and half will be utilized by the children processes. Another situation can be children share the subset of parents' resources. Children may not need all the resources that the parent have. They may need some of the resources. For example, they may not need the input-output devices that parent have. They only need to be executed on CPU. So children sometimes may not require all the resources that parent have. They may require some of the resources, subset of the resources that parent hold. Either they can share all the resources of parents, or they can share some of the resources, the subset of the resources. And there can be a situation when parent and children share no resources. When parent treat children processes as independent process and ask them to request their own resources from operating system. So this is the third case. When parent do not allow children processes to ask for the parent resources. Instead, parent process treat children process an independent process and ask them to request operating system for their own resources. So how resource can be shared between parent and children? Three conditions can be there. Either children share the resources held by the parent, or children share the subset, some of the resources that their parent have, or children process are treated as independent process and they would request their own resources from operating system. Parent would not give their resources to the children processes. Now, how execution of parent and children process can be done within the system? Again, the situation can be parent and children execute parallelly. They execute concurrently. For example, in the case of websites, If you click some link within one website, another website on another page gets opened and both the pages are now running. So parent is running along with its children process. Both are running concurrently. And in some cases, you can either first close the parent and children process will keep on executing. But in some cases, parents need to wait until children gets terminated. You cannot close the parent. If you close the parent, children will get terminated. For example, in case of programming, when main function is executing and it calls function A, which is a child process. Now, if you close main process, the child process will not get executed. So parent has to be there in order for the child to complete its execution. The child gets terminated first and results are then given back to the parent. Then parent can be terminated. So both the situations are there. In some cases, such as in websites, if parent process generates a child process, so you can close the parent process and child process keeps on executing itself. But in some of the cases, when parent process creates children processes, then if you close parent process, the children process will not be able to execute. So for that, you have to keep the parent process running in order for the child to get execute, terminate, give results to the parent, and then parent can be terminated. So this is the situation when forking occurs, how parent and children process can be executed and how the resources can be assigned to them. If it is a single process, the situation is very complicated. But when there is forking, so these things may happen in your system. Now, process termination in case of forking is again quite complicated. If it is a single process, its termination is easy. Either normal termination would occur or abnormal termination would occur. We had discussed both the types in previous lectures. Normal termination is when a process executes last statement and then it asks operating system to terminate it, to delete it, or to exit it. This is the sequence or the pattern of normal termination, that a process completes its execution and asks operating system to terminate it, to delete it, or to exit it. Now, when it is the case of parent and children, how termination would occur? So, parent normally asks the children to give results. So, output data from child to parent. So, children give their result to parents and parent wait till the time children would give them result. So once children have submitted their results to parents and children get terminated, now the parents then compile all the results are given to the user, and then parent process gets terminated. Before termination, all the resources held by both the parent and the children are deallocated by the operating system. So if they are using CPU, that is being taken back by the operating system. If they are using RAM, if they are using other devices, all the resources are taken back by the operating system from those processes, both the parent process and the children process. So these are the activities that are generally done before a process gets terminated. If it is a parent process, it would wait for the children to give them results. Children gets terminated first. The parents then returns back all the resources it holds to operating system and request operating system to terminate it or to delete it. Now, in some cases, parent may terminate the execution of children process, which is the case of abort. Abnormal termination we discussed. In some cases, when children processes are not functioning normal, so parent can kill their children processes. Now, in what situation this can happen? For example, if a child process has exceeded allocated resources. That means a child process is requesting for some resources again and again, and parent process is not able to fulfill its request so oftenly. So in that case, that means the child is creating trouble for the parent process. So that child process is then by force killed by the parent process. So this is the case of abnormal termination. This was the first situation, was the case of normal termination, and now we are discussing when abnormal or abort can happen. So when a child process requests some resources again from parent, so that means it is creating troubles for parent process. So in that case, parent process can kill that particular child process. So, or this could be one of the reasons, or another reason to abort a process, a child process, is the task that has been assigned to that particular child process is no longer required. That means the activity that we wanted the child process to complete is no more required, or the results of that particular child is no more required. So in that case, a parent process can kill or abort that particular child process. So both the cases can be there. If child process is problematic, parent can kill that child process, or if in the case when the task that has been given to the child process is no more required, so in that case parent can kill or abort its child process. And now when parent wants to terminate, when parent has to exit the system, leave the system, so in some of the operating systems, they do not allow child to continue if its parents terminates. So some of the operating systems do not allow children to keep on running if parents is getting executed. So they have to kill first the children, and then parents get aborted or parent gets normally terminated. For example, in programming, as I just said, if you want to kill the main process, so children processes main function. So the children function A, B, C, Cn function, C out function are not be able to be executed on their own. So if parent main function is getting terminated, so children will have to be terminated, no matter if they have completed their execution, if they are in the middle of their execution, or if they have not yet started their execution. If parent is terminating, the children process have to be terminated first before the parent. So before the parent is terminated, before the parent gets exited, all the children are terminated first. That is in the shape of cascading terminated. That means the child that was created first will be terminated. Then the second that was created second will be terminated in shape of a cascading termination, and at the end parent process will be terminated. So this is the case of, in case a process terminating when it has forked some children. So the termination will be happen in this manner, either normal termination or in case of abnormal termination. Now the next topic within this chapter that we are going to discuss now are what is process scheduling, how a process can be scheduled to stay in some of the device, or how it can be scheduled to be executed on CPU. So these are some of the subtopics within process scheduling that we are going to discuss next. Now, what are the scheduling queues? Scheduling queues, process scheduling queues, that means there are some queues at various locations within your system in which processes are waiting in queue. Processes are waiting one after another in a line, in a queue. So some of the queues are there within your system. The first queue that is very common is known as the job queue. That means job, as you all know, are the user tasks which are not currently being running on CPU. So those user tasks are known as job queue. That means all of the process within the system, that means within the system at your secondary storages, are known as the job queue, because the processes or the user tasks are stored there in shape of a queue. So your disk is organized in shape of queue. Processes or jobs are organized there one after another. So first queue where process wait is the job queue. Job queue means that is not an active process which is not currently executing. So jobs are created on your disk, on your any removable storage device. So there the processes or the jobs are waiting one after another in shape of a queue. Another queue that is formed is the ready queue, which is your RAM. Ready is your RAM. So all the processes residing within RAM or main memory, and they are ready to be assigned to CPU. So here in RAM, jobs again are waiting in queue one after another for their turn to be, they are ready for their, but waiting for their turn to be assigned to CPU. And then other queues are there. Every device that is attached to your system stores processes in shape of queues. For example, you have a single keyboard. Multiple processes may require input at the same time, but since keyboard is one, you can give input to one process at a time. So other processes are then waiting for their turn in that particular queue, of input device for their turn. So every device, keyboard has a queue, so processes that require input will be waiting in keyboard queue one after another. So you would get input to one process, then another process, then because you have a single keyboard. Similarly, all other devices attached to your system are single instances. They are single resources. So they the process requiring those devices need to wait in that particular device queue. For example, printer. If you connect printer to your system, you can easily see the status of that printer on your taskbar. If you have clicked more than one application for printing at the same time, but printing will happen one after another. One document will be printed first, then second document printing will be started. So you can clearly see the queue of printing on your taskbar. So these are three different types of queues where your process waits. The job queue, that means any other storage devices other than the RAM. The ready queue, which is the queue within the RAM, and every device in your system is organized in shape of queue. Process wait there in shape of queue, one after another. And a process migrate between these three types of queues during its lifetime. We are going to see the diagram how a process moves between these different types of queues. So this is the structure of different queues that we just discussed. These are the queues. Here you can see the ready queue. This is the RAM. The structure of the queue is in the shape of the data structure queue. It has a head and a tail, the top and the bottom. Insertion from the tail and deletion from the top, the queue, the stack the data structure that you have studied. Then you can see magnetic tape. The queue is for another secondary storage, magnetic tape. Its structure can be seen here. Another unit, I had also told you, memory is a single resource, but it has multiple instances. So magnetic tape are having two instances here in this case. Two magnetic tapes are connected to the system. That means, so two queues will be there. Then the disk, if secondary storage, a disk is there. So you can see a queue for the disk as well. And then the device queue, the terminal, the output unit. the terminal unit, you can see a queue here as well. Now the structure of this queue is organized in shape of a linked list. Here you can see like this. This is in the shape of linked list. So the head will point to the first process that is stored at the top of the ready queue. I am explaining the structure of the ready queue, that means the RAM. So here you can see the first process that is stored in the RAM is process 7 along with its PCB. So you can see the PCB here, all the information within the PCB are also stored along with the process. Now you also know the structure of linked list is twofold like this. It has two parts. The first part is the content part, while the second part shows the next part. Content shows the content of current node, while the next part shows the address of next node connected to this node. So here you can see the next part is connected to process 2 along with its PCB here. So this node is storing not only the process but also its PCB along, while the next of this node is represented with earthing symbol. That means it is the last node. The next part is empty. Its next part is empty. So PCB 2 or process 2 is the last node. So currently within the ready queue you have two processes. At the top is process 7, while at the tail is process 2. Here you can see the head is pointing to first process and the tail is pointing to the last process. There can be so many other in between the head and tail, but the head will point to the first process and tail will point to the other to the last process. The structure is defined in shape of a linked list. A linked list, within linked list, every node has two parts, the content part and the next part. The content part stores the content of current node and the next part stores the content, the address of next node. So the first part stores, the content part stores the content of process 7, while its next part stores the address of next node, which is process 2. So this is the structure I have elaborated for the ready queue in magnetic tape unit 1, unit 2. That means two magnetic tapes are connected to your system, and here you can see the head is empty and tail is empty. Both are showing the earthing symbol. That means currently both the magnetic tapes are empty. No process is stored within the magnetic tape. Now the disk, your storage unit disk, is having again three processes. Here as you can see, the head is pointing to process 3 and the next of process 3 is connected to process 14 along with their PCBs, while the next of process 14 is pointing to process 6 along with their PCB, while the next of process 6 is empty. That means this is the last process in the disk queue, while the tail is pointing to the last process. Similarly, the terminal, the output unit, it is again in the form of queue, since you have single terminal, single output unit at the time. So the head is pointing to process 5 and its next is empty. That means only single process is waiting for the terminal, and tail is also pointing to the same process. That means only a single process is currently waiting for the terminal. So this is how the structure of queues are organized, and a process moves between these different types of queues. How they move between these different types of queues, let's see this with the help of another example. Here you can see a process moves or migrates between these different types of queues. Here you can see a new process created and it is inserted at the tail of the ready queue. Now when its turn is to be executed on CPU, so its states is change from ready to run. It is assigned to CPU. Now if it executes or completes its instruction, so it gets terminated. Here it is going out of the system. That means it is getting terminated either normally or abnormally. Now for example, currently it is not getting terminated, so different situations can be there. For example, it goes to blocking state, request for some IO device, and if that particular IO device is not currently available, so this process will have to wait in the queue of that particular IO device. And then once it executes, it is executed on that particular IO device, execution is completed, it goes back to the tail of ready queue again. So from the device queue, it has come back again to the ready queue. Now for example, this is not the case. Another case may be that its time that has been assigned to it to be executed on CPU, the CPU time that was assigned to it gets expired. So it then goes back to the tail of ready queue again. If this is not the same situation, then next case can be that it creates its children, forking, that we just discussed in previous slides. If it creates children, so it then has to wait before its child gets executed. So once the child is executed, now the parent, because the CPU time has been assigned to the children, the time that was given to parent has been assigned to children, and then parent then has to wait at the tail of ready queue for its turn again to be executed on CPU. If this is not the case, the last case can be if some other interrupt occurs. For example, some download gets completed and you get a signal that a download is completed. So current running process is stopped and you give an operating system gives or pays all the attention to that interrupt, to that download. So the download will be then get completed, or the time given to that particular process is given to the interrupt or that download. So that process then has to wait for its turn again at the tail of ready queue. So the interrupt can be from within the process itself, or it can be from anywhere within the system. So operating system pays attention to that interrupt. When interrupt happens, completes, the process then goes back to the tail of ready queue and waits again for its turn to be assigned CPU. So this is how a process keeps on traveling or migrating between different queues. It first reaches the ready queue, then it goes to the device queue, and then back to the ready queue. Okay, now here it comes to ready queue. It may come to ready queue from job queue. You can open some process from your disk. It may happen. So actually you have opened a process from the job queue. From job queue, it comes to the tail of the ready queue. So it may happen either you create a new process or you open already stored process, the process which is already being stored on the disk. So you can open your process from disk. So in that case, you are actually opening a process from the job queue. So this is how a process travels between different types of queues that are present in your system. Now within process scheduling, we have discussed the scheduling queues, the different types of queues that your process travel in between. The next topic is the schedulers. What are the schedulers that perform the scheduling task for the processes? Schedulers have specific functions. They perform specific tasks for operating system on behalf of operating system. Actually, schedulers are functions of operating system that perform specific activities. So there are two types of schedulers. There is one more which I'll be discussing later on. So currently, for the time being, I'm discussing the two, the long-term scheduler, which is also known as the job scheduler. Long-term scheduler or the job scheduler, as the name shows, job. That means this scheduler is related with the jobs. So what does it do? It selects which processes should be brought into ready queue from the job queue. So long-term scheduler or job scheduler selects the processes on the disk and select which one of them should be brought to the RAM. This is the duty of job scheduler, or we can also call it long-term scheduler. Now, why it is known as long-term scheduler? We'll be discussing that later on. Another scheduler is known as the short-term scheduler or the CPU scheduler. That means the processes which are to be executed on CPU. So short-term scheduler plans activity for those processes. So what does it do? It selects which process should be executed next and allocates CPU. That means short-term scheduler organizes the ready queue. Short-term scheduler organizes the RAM. Which process should be executed first? That particular process is taken to the head of ready queue. So short-term scheduler, the task of short-term scheduler is to reshuffle or to shuffle the RAM on the basis of the priorities of processes. So which process should be executed next? That process is taken to the top of the ready queue and then CPU is assigned to it. So these are two schedulers, the long-term scheduler, which selects among different processes stored on the disk which process should be brought in RAM, while short-term scheduler organizes the RAM in order to make it easy for operating system to select the process which is at the top or ahead of the ready queue to be assigned next to CPU. So short-term scheduler organizes the RAM, the ready queue. Now there is another scheduler, as I just said, there is midterm scheduler as well. The task of midterm scheduler is swapping. It swaps out a process out of the system to some secondary storage, to virtual memory, and then when it is required back, when that particular process is required back, that process is then swapped in by the midterm scheduler from the secondary storage, from the virtual memory back to the system or the RAM. So this is done, the swapping activity is done by the midterm scheduler. Here you can see. So a process is in ready state, it is executing, it is being executing, and for some of the reason it is swapped out or suspended. So that suspended process is then swapped out of the system by the midterm scheduler, and when it is required back, it is then swapped in again by the midterm scheduler to the tail of ready queue. So swapping function is generally performed by the midterm scheduler. Midterm scheduler, swapping may not or suspension may not always be required. So midterm scheduler may not be that active as the long-term or short-term scheduler are. So this is the entry of midterm scheduler. Midterm, the task of midterm scheduler or the activity it performs is the swapping. It swaps out a system to secondary storage, and then when it is required again, it swaps it in again within the system or tail of the ready queue. Now, why short-term scheduler is known as short-term and why the long-term is known as long-term? So this is the reason here. Short-term scheduler is generally invoked very frequently as you open so many processes at a time and they are stored in a queue in RAM. So short-term scheduler very quickly swaps the processes, very quickly organizes your RAM, which one to be executed next. So short-term scheduler is quite fast. It works or it gets invoked in milliseconds. That is why it is known as short-term scheduler. It is quite quick or required very oftenly in the system. Since a user opens a lot of application at the same time, now which one to be executed, it is on the wish of user. It is on the basis of user priority. Short-term scheduler then shuffles the shape of the queue of the ready queue. Which one you want to execute first, though you have opened it last, but you want that application to be executed first. So this short-term scheduler selects that process, takes it to the head, while the head process is then taken back to that particular process place. Now the long-term scheduler, why it is known as long-term? Because it is invoked very infrequently. Normally the time it takes is within either seconds or even minutes. It is quite slow. Why? Because you only once require to open applications from your disk, only once in a minute, once in quite a long time. So that means long-term scheduler is required very infrequently, but short-term is very quick. Long-term only when you require to open some application from the disk, only then long-term scheduler gets activated. So its duration of activation or invoke, when you require it to be invoked, is very slow. Maybe in minutes, maybe in hours, maybe in seconds. Only when a user wants to open an application from the secondary storage, only then long-term scheduler gets activated. But the important point, the long-term scheduler controls the degree of multiprogramming. Degree of multiprogramming means how many processes should be stored in RAM at the same time. This is degree of multiprogramming. Now this degree of multiprogramming is controlled by the long-term scheduler. If long-term scheduler wants, it can allow you to open more than one applications at the same time and store them in RAM. If there is no long-term scheduler, that means one job at a time will be arrived in RAM, which is the case of batch system that we had already discussed in chapter 1. So with long-term scheduler, it controls the degree of multiprogramming. That means how many jobs, how many processes should be loaded in RAM. That is being decided by the long-term scheduler. So when you click 4, 5, 10, 100 applications one after another, that means you are actually invoking long-term scheduler, and it is taking those all applications from the disk and getting them in RAM. So the degree of multiprogramming, if long-term scheduler is not there, your system is again a batch system. Only one job is residing in RAM. Now we have two types of processes. Some processes are IO bound. That means they spend more time on IO devices and less time on CPU. And some processes are CPU bound process. That means they spend more time on processing, more time on CPU, while less time on IO. So these are two different types of processes. The last topic that we are going to discuss within process scheduling is what are or how we can change the context of from one process to another. So context switch within process scheduling is your next topic. Here you can see context switch means changing. You have single CPU. So once at the time one process is executing, so when it is time to execute another process, so here context is switched from one process to another. One process is having different set of instructions doing different functions, while another process is having totally different functions, so totally different sort of application is it. So Changing context from one process to another, that means assigning process to CPU one after another, is known as context switch. So this is generally done by operating system. So I have discussed it with the help of this diagram. Here you can see in ready queue you have two processes, P0 and P1. They are stored in queue one after another. So when it is time for P0 to be executed on CPU, during that time P1 is waiting. Here you can see P1 is waiting for its turn and it is waiting in ready queue. Now when it is time for P0 to stop its execution due to whatever reason, due to timeout, due to some interrupt or whatever reason, so once it is stopped before assigning CPU to the other process, so operating system saves the state information of that process in its PCB. For example, the program counter is updated, process name, process state, all is stored in PCB, and the PCB of next process which is currently waiting is loaded. Here you can see it is loaded. For example, from where this process has to start execution, what was its current state, all the information is stored in PCB. So its PCB is loaded and CPU is assigned to the next process. Now here you can see P1 is executing on CPU now, and during that case P0, when it completes its request on IO or whatever interrupt or whatever was the reason for its stopping, when it is over, it comes back to the tail of the ready queue and waits there. So in that time it is idle waiting for its turn. Now when it is time to stop P1, for example, its time slice is expired, so before assigning CPU to the next process P0, which is the previous one, so the state information it's saved in its PCB, in its respective PCB, for example, from where it has to continue execution. So instruction, the address of that instruction is stored in program counter, that is stored within the PCB. All other related information are first stored back, or the PCB is updated, and the state information of the previous process P0 is then reloaded from where this process should start execution. So all the information is then reloaded and CPU is then assigned to the first process. Here you can see, and when the first process is executing, the second will then have to wait for its turn within the RAM. So in this way, switching is done from one process to another. One process is when executing on CPU, the other process waiting for its turn in RAM. And when it is time to stop first process, before assigning CPU to the other process, PCB of that currently executing process is saved, is updated, and the PCB of the next process is then uploaded. Operating system sees its PCB to know from where it has to start execution. So then the CPU is assigned to the next process, and when it is time to store the next process, now before assigning CPU to the first process, again you have to update the PCB of currently executing process, and then the PCB of the previous process is loaded back and CPU is then assigned. So in this way, if it is two processes, it is three processes, four, whatever processes are waiting in the ready queue, context switch is happened in this way. That is all for now. This is the end of second chapter, processes. The points that we discussed in this chapter were: we developed understanding with the term process. We discussed different states that a process shows during its lifetime. We discussed the state transitions, how a process changes its state from one state to another, what activities are, or what functions or what events require them to change their states. We discussed them diagrammatically. We discussed different operations that can be performed on processes in detail. Then we discussed the scheduling information, how a process scheduling information is controlled, that is stored generally in process control block. And then how a process scheduled. For example, what are different process scheduling queues? We discussed different types of scheduling queues. We discussed different types of schedulers that perform the scheduling function for the processes. And then at the end, we discussed how a context is switched between two processes when it requires to be executed on CPU. Since you have single CPU, at the time, one process will be allowed to be executed on CPU. So you have to require the context switch activity to happen, and this context switch is controlled by operating system. That is all for now. I hope you have understood the discussion we had done in this chapter. If you have any query, you can email me or ask me on KCMS. I thank you all.